Hello, everyone. I'm Xinyu from Peking University. It's my honor to introduce our recent work in Perennial Safety International Conference. The topic of this talk is enhancing computational fluid dynamics simulations through GPU-accelerated sparse matrix solvers in OpenFOAM. And there is the outlines of this report. In combustion simulation, there has long been a trade-off between accuracy and efficiency. Currently, in the engineering field, RANS and the LES method have been widely applied. However, these models, which contain many physical assumptions, are increasingly unable to meet the requirements for detailed numerical simulations under extreme conditions. While the DNS method, direct numerical simulation, is a first principles model for combustion, but is still considered a computationally unaffordable simulation method. Currently, the field of combustion is using AI and GPU efforts trying out advanced AI algorithms and high-performance computing power to address the accuracy and the efficiency trade-off. Firstly, AI algorithms are currently maturely applied in combustion chemistry and other simulation aspects. And on the other hand, safety platforms are actively being ported to high-performance many-core hardware for acceleration. Therefore, it can be seen that AI and HPC technologies are making the detailed chemically accurate DNS affordable. And a lot of works have been done in AI and GPU-assisted combustion, including the GPU-accelerated chemistry and the GPU-accelerated safety platform and the AI-accelerated chemistry. However, current research lacks support for the combination of AI and the GPU methods, large-step implicit solving method, and studies on related parallel algorithm. Therefore, this work wants to develop an integrated framework that supports both GPU acceleration and machine learning models. The detailed objective is we will complete the fully porting of combustion simulation software to GPUs. As shown here, all the time advanced operations will be conducted on GPU. And the specific computational pattern includes the implicit PDE, NN inference, Newton's method, and high-order temperature polynomials. Now, we need to introduce the code baseline. DeepFlame is the first large-scale open-source platform that couples AI frameworks for simulating reacting flow. And this figure shows the main features of DeepFlame. It is constructed based on OpenFOAM, Cantera, and LibTorch. Here is a GitHub link of DeepFlame. You can find more information here. However, in terms of hardware support, DeepFlame currently only supports heterogeneous computing for the AI module. And next, we will show our detailed implementation. First is the PDE part. The PDE solving contains two parts: matrix construction, namely the implicit FVM discretization, and the linear system solving. In general understanding, solving linear system is typically the most time-consuming task, and there are lots of third parties developed by math and HPC community, such as the AMJX, the cuBLAS crossover, it should be noted that the AMJAX swapper also makes AMJAX available in OpenFOAM. And follow the date method, DFlame also utilize AMJAX in solving PDEs. But however, as shown in the right figures, we can observe that actually the time spent on matrix construction is comparable to or even longer than the time spent on linear system solving. But there is currently no solution for accelerating sparse matrix assembly, despite their often dominant role. So we decide to work on this topic. Then I will briefly introduce the matrix assembly process in OpenFOAM. The matrix assembly process mainly build the coefficient matrix A and the source term vector B. And here we show the relationship between matrix and mesh. The matrix A of linear system is n multiplying n, where n is the number of the mesh cells, and so is the dimension of X and B. Then we need to know that cells are connected to each other through internal phases. Each phase has an owner cell and a neighbor cell. Then we take a look to the matrix. We can see that most coefficients in A are zero, except the owner, diagonal, and the neighbor coefficients. This format of matrix is LDU. The lower, upper, and the diag are stored separately. And here we show the procedure in solving PDEs. First is constructing the LDU matrix. Here is an example in discretization of Laplacian term. As seen in this line, the upper and the lower entries are directly obtained through the multiplication of phase values. And that's why use LDU format in constructing matrix is quite convenient. And the format of matrix need to be converted from LDU to CSR or LDU to ELL, because the LDU format is not suitable in linear solving procedure, such as SPMV, sparse matrix multiply vector, one of the most important operation. And the CSR and ELL formats significantly improve performance over LDU format in the linear solving procedure, especially for SPMV operation. Then we can use AMJAX to solve the linear system. The input is AXB and the output is the new X. Recently, we have developing an independent solver program, which is named the DF Linear Solver, and have mirrored the OpenFOAM's implementation of BICG step and PCG solvers to GPUs. Then I will briefly introduce the preconditioner in DF Linear Solver, GAMG. Geometric algebraic multigrid. Compared to AMJAX, we implemented the geometric multigrid, which can bring significant performance improvements. In detail, GMG integrates geometric and algebraic information to construct efficient multi-level grids and preconditioners. This approach significantly accelerates convergence, is highly scalable for large problems, and offers flexibility across various linear systems. And we use GMG as the preconditioner for the PCG solver to accelerate the algorithm's convergence. Next, we will briefly introduce the conducted optimization. First is the DNN innovation. We adjust the inference batch size, reduce memory footprint while ensuring fast inference speed. And here we can see that when the batch size is set to about 8,000, the inference procedure features acceptable performance while keeping a quite low memory footprint. Also, we adopt mixed FP16 precisions in the inference procedure. Next is the CUDA kernel. The optimization strategies can be mainly divided to two parts. First, the memory banded functions adopt a data coalesced approach to enhance data locality and reduce memory access overhead. And for the compute bounded functions, optimized by using memory instead of computation, splitting kernel, and we utilize the constant and shared memory. And finally, we can see that all the kernels show a good performance and near the hardware limit. And here is our parallel approach. We adopt one core or one card process resource allocation method, and we use NCCL for direct GPU to GPU communication between processes and reducing data copying between the CPU and the GPU. And here is the progress we have made so far. The implemented schemes include the DDT schemes, interpolation schemes, and the DIV scheme, and etc. The implemented boundary conditions includes the empty, zero gradient, fixed value, periodic, and processor. And the implemented solvers includes the AMJAX, BICG STAPE, GMG PCG with CSR and the ELL matrix format. Now we will introduce the results. First is the reactive Telegreen vertex. It is a recent built combustion benchmark. It can be seen that the simulation results from the GPU DNN is the same with the CPU CVOD and other results from the other state-of-the-art codes. And now is the performance from this figure. It can be seen that the 4V100 V100 GPU achieve nearly 35 acceleration compared to a 32 core CPU. And here we give a breakdown of the PDE solving procedure. It can be seen that the implicit discretization part get nearly 75 acceleration, and the solving part, which is conducted by AMJAX, achieved a 4.3 acceleration. By further using GMG PCG to solve the P equation, we achieved an additional 5 acceleration compared to using AMJAX for solving the P equation. And here is the memory footprint. It can be seen that the memory usage for 4 million grids is controlled with 10 GB, and only half of the memory usage increases with the number of the grids. And additionally, it can be seen with the use of the CUDA stream allocator, the memory footprint of safety data get reduced of 2.27 times. And there are some other results. The laboratory scale turbulence cases can still achieve high simulation accuracy, and a single card can handle LAS cases with 2.5 million grids. In this project, we implemented the full process GPU fully implicit simulation solver that integrates AI methods. The specific porting tasks include the implicit PD solving, neural network inference, and thermal property calculations. And the correctness and efficiency tests were conducted on standard and lab scale cases, demonstrating that the AI plus GPU method can achieve acceleration by 2 orders of magnitude. And we implemented the common boundary conditions and the numerical schemes. And we replaced and optimized AMJX to further enhance overall computational performance. And for the future work, we plan to conduct large-scale scalability tests, and we plan to conduct tests across multiple platforms architecture and packaged for OpenFOAM and DeepFlame communities to reduce usage complexity. And that's all. Thanks for listening.